Hello everyone, welcome to today's workshop. My name is Sarah Lynch and I'm part of Altair's global academic team. It's my pleasure to welcome you all to our third of 3 workshops for our 2024-2025 Altair Global Student Contest. Albert, if you go to my first slide here, I would like to introduce my colleague Albert Dunford here. He's the director of the systems modeling group of Altair's global technical team and also our all-time PSIM specialist. So we're really thrilled to have him here today and present to you guys. Albert will guide you through this session called Mastering Power Flow in Robotics, PSIM Essentials for the Altair Global Student Contest. So this session is designed to help you and other students like you to understand how to leverage PSIM for the optimization of your robotics projects in an electrical sense basically, and power flow sense. And then you can hopefully get a better idea on how to prepare your entries for a contest, or just to generally know how to do this to improve your robotics behavior or components. Before we dive in here, a quick reminder about the contest itself. If you haven't already, please go visit our Altair Global Student Contest page to explore all of the details, the guidelines, the prices, and everything else, but I have done a little summary here on the slide. So you can see the topic is robotics optimization, and we want to want you guys to show us how you use Altair software to build better robots faster. And any student who is actively enrolled in any educational institution can be part of our contest and submit an entry. You can see here we have 3 prizes per quarter. The first prize is for $2,000, the second prize $1,000, and the third prize $500. And per quarter means the quarters of our contest, which the first quarter is running right now. It started in October and will end on December 31st, 2024 at 11:59 p.m. And a little hint on the side here, if you are one of the first people to submit here in our first quarter, this is going to be a much higher chance to win, because a lot of the teams and a lot of the students worldwide, they're, as everyone's still preparing and figuring out what do they want to submit. So the first section of our contest is usually the one that has a few less participants. So if you have already worked with our software, I can only recommend to create a contest video as soon as possible and submit it before the end of the first quarter for even higher chances than normal. On the right here, you also see the additional prizes that we have. We will, during this whole contest, award 3 FIRST team sponsorships at $5,000 each. If you guys submit a testimonial video in which you tell us how you've used Altair tools before, why you love them, and why you would love Altair to sponsor your team. And we can use those videos then to promote your team and also to get to know you and award you a prize potentially. If you're not on a FIRST team and you're a normal university student, we also will give out 3 Altair student ambassadorships in which you can be a student ambassador for us and earn up to $1,000 per ambassadorship. So this is just a little side hustle basically to the contest. And if you're a student, you would do also a testimonial video about why you love Altair software, what you have used it for, and why you would be a great Altair student ambassador. If you go on our submission page, you will see some example videos for contest entries as well as for these testimonial videos. So if you want to have a little inspiration of how this could potentially look, go check that out. And yeah, that's the good things that you can win here if you are submitting during the contest period, which as I said, first quarter ends the end of December, and then the second quarter starts in January, ends the end of March, and the third quarter starts in April and ends at the end of June, and then the contest is over. So that's your opportunities to submit and win. I think that's basically all I wanted to tell you about the student contest. But with that, let's get to the good part. And I know that Albert has a fantastic presentation prepared, and I'm excited to learn from his expertise, and I hope you are too. And with that, Albert, it's all yours. Take it away.
Perfect. Thank you so much, Sarah. Hey, can you run that poll? I'm curious to find out if people are in high school or in uni or what competitions. 88% have voted, and it's 29. Okay, it's mostly uni. It's 60% university. Okay.
Yeah, if you are part of any kind of competition team, please let us know which one. I have listed here our main ones that usually use PSIM for their work, but it looks like lots of FIRST people here. Okay.
Yeah, thanks. Thank you, folks, for supplying the information. Okay, so many of you said that you're in university, but then when it comes to the actual competitions, it looks like most of you are in FIRST Robotics. So I will try and, so a lot of the beginning of this kind of talk is going to focus mostly on very simple modeling techniques that can be applied by people who are not very technical, and then I can set the stage for a more comprehensive and more technical approach that can happen for the university kids. So yeah, I think I was kind of expecting those kinds of numbers. So let's get cracking here. So basically, we want to look at power flow. So a overarching question or concern in FIRST Robotics can be on power cycles, on breakers or fuses blowing out or tripping as a result of whatever you're doing during the competition or the contest. This would be a similar issue for larger robots as well, or electric vehicles. This is a point of concern when it comes to power flow and overcurrent protection. I think it's particularly interesting for the FIRST Robotics kids, and we'll get into that as well. So, and I've got some more advanced methods and techniques towards the end as well, which would be more applicable to university teams. So let's keep crunking along here. So I'm a power electronics specialist. Okay, so I'm going to kind of preach a little bit about power electronics for maybe just a couple minutes, so you get a feel for what we're dealing with here at a fundamental level. Power converters and power electronics. It's a translator of modern electricity. So if you think about it, the grid is an AC system. It's got a, if you don't know what AC is, it's a wavy voltage waveform, and the voltage that comes out of the battery in your phone or whatever is DC. We need to make conversions here between all these things, and it needs to be efficient. All modern motor drives are based on power converters and power electronics. And I'll show you in a little bit here. So lots of different optimization goals, performance, cost, etc. But it's the world is increasingly more and more reliant on power electronics. And if you look at trends, people are suspecting that the percentage of energy that will be translated by power electronics, 10 years from now may be over unity. So there'll be multiple conversion points for all of the energy that gets generated and then used by the general public. So a growing industry, etc. Here's a little kind of conversation point here. So coming out of your batteries, in your robot or whatever, it's DC. But most modern motor drives, or all of the motor drives that you're going to be using in your competitions, will require waveforms that look like this. These are what's being used in the brushless DC motors now, or a variation on this theme. And another point here is so this is what comes out of the wall, and this is what you need by your phone needs this thing to charge. A lot of the electronics in your computer, all of the electronics in your computer run on this. Yeah, essentially, if we don't match things up to what we need, the best case scenario is that it just doesn't work. The most likely scenario is that it will catch on fire or blow up or burn. Okay. So PSIM is a tool specifically designed for power electronics and motor drives. I am not going to sit here and talk to you about power electronics today. We're going to try and greatly simplify modern power converters into very easy to model steps. And hopefully those will then be something that you can apply to form system simulations that will allow you to understand and come up with some reasonable power flow simulations. So again, what is a motor drive? A motor drive is your battery, and then you've got your inverter. This is what's converting. We go back to my original slide where we have the single flat line and we have the 3 wavy lines. This is what's doing that translation, and then we have our motor, and then we've got our control. So the control is the brain that tells the things what to do, and basically we're converting electrical energy into mechanical energy, electrical power into mechanical power. It's still watts, joules per second. It's still watts, but it's just electrical or mechanical. Yeah, so let's do a demo. Let's do a demo.
Oh yeah.
So this is PSIM. Let me close that down. And this is a motor drive. Okay. So this is a design suite in PSIM. So if you open up or download PSIM, you can go in here and open up a motor drive. And these are template motor drives that you can play around with. The algorithms that are at play here are typically taught in master's programs. They're not usually covered in undergraduate, so I'm not going to get into the theory here at all. We're just going to kind of look to see how this sort of stuff works. So we can just, yeah, so what I've done here is this is the first one, the IPM drive, and you can just open it up and click simulate, and it's going to run the simulation, and we're going to see what comes of this. So we can see this is a speed control system, so we're trying to get the thing to run up to 8,000 RPM, and then we can also see the amount of torque that gets developed, and so we can see we're generating close to 1,000 Newton meters of torque, and then our steady state torque is at the bottom here at 150 Newton meters on the blue here, and then we talked about those wavy lines. So here are those wavy lines. So when we're driving the motor, we've got those 3 wavy lines running, and then if we look, we can see that at low speeds, those wavy lines are slower, and then at high speeds, those wavy lines are closer together. They're higher frequency. So the rate of change on these waveforms is kind of dictating the speed that the motor spins at. And so this is what field-oriented control is. So I think, you know, for the FIRST kids, if you look at some of the motors that are available, like from Kraken, they'll have like FOC control. This is FOC control. This is what we've got going on here. And that's kind of the extent of the physics and the theory I'll get into. But this is what we want to do, is convert this complex simulation into something simple so that you can kind of analyze it and look at it yourselves and start to understand impact on breaker ratings and overcurrents and all that kind of stuff. For the more advanced kids on the call and doing university, you know, this, you can, if you're doing your own motor drives, you can punch in numbers here, and there's a lot of tutorial videos that go over these kinds of concepts, how to put in these numbers and parameters for your motor and for your system, and you click update parameter file, and it gives you some information here about what it's done. You can also click on this button here, which gives you your speed torque curves. So this is the speed that's available to you, and the torque available, and the system power here. So one concept that's pretty apparent is, regardless of, you don't always get the same amount of torque. So there's a torque rating at stall at 0 RPM, and then there's a power limit that runs here, and you get decreasingly less amounts of torque at higher speeds. And this is just a function of the power limit. So there's a bunch of limitations that go into electric motors and their systems, you know, current, thermal, mechanical stresses, all that kind of stuff. So this information can pop out for you there. Now, thankfully for the FIRST kids, you don't got to worry about that. So let's go back to the slides and let's kind of talk about this here. So how can we simulate power flow? So we just saw in that simulation where we had DC being converted into a mechanical power. We were driving mechanical load. We ramped it up to 8,000 RPM. So like I said before, electrical power is getting converted to mechanical power. Electrical power is volts times current, amps. Mechanical power is shaft speed, the rotational speed, times the shaft torque in Newton meters. So radians per second for the shaft speed times Newton meters. So we can think of it in a very similar way. 1 volt equals 1 radian per second, and 1 amp equals 1 Newton meter. And the key translation point here is how much torque do I get per amp, essentially. So how much torque, if I give my motor 10 amps, how much torque am I getting out for that constant? That is the fundamental kind of concept we're going to work on here to develop some simple models that are going to help us look at power flow. If there's questions, write them down. If I'm going too fast, let me know. Okay, so coming in here, the torque constant, it's Newton meters per amp. So some basic math here. So if we have a torque constant of 5 Newton meters per amp, if I apply 10 amps, we go 10 amps times 5 Newton meters, and then we all remember we can cancel the units. So the amps cancel, and then we're left with 50 Newton meters. Okay, I hope that makes sense. 50 Newton meters. So basically, you multiply your torque constant by the current you're applying, and you get a torque value out. Okay. In high performance motor drives, this constant is not a constant. It changes. However, for FIRST, the motors that you guys are using are so overpowered, you don't need to worry about it. You can treat this as a constant. And so that's our first approximation for FIRST kids is torque constant is a constant thing. For people doing Formula SAE or other more advanced robotics applications where you need to get into really high speeds or very high power systems, this number changes, and we'll get to that a little bit later. So I've pulled up one of the motors that is used by FIRST. It's this Kraken motor. It's a bit of a beast, if you ask me. It can do over 1 kilowatt. And it can do, it's got a stall torque of 7 Newton meters. It's got this spline, excess shaft, versatile mounting options. But for FIRST, the power distribution hub you use is rated for 40 amps. So you can only use 413 watts of this thing. It has an efficiency of 80% at 30 amps. So there's a couple of points here. So let's kind of dive into these specs in a little bit more detail. And that's this other page off the Kraken website is the torque constant down here. So this is in millinewton meters. And this is so for every amp you're applying, you're getting 19 millinewton meters with the Kraken FOC. FOC stands for field oriented control, which is the modern method of driving motors. I'm not sure what these other control methods are. I didn't look into it specifically, but the Falcon here, FOC, is running 18.33. In general, the bigger the number, the better, because you want torque. Torque is what's going to do your work for you. It's going to allow you to accelerate your mechanical systems fast. It's going to allow you to do the work. So, let's do a little bit of math here. And if you recall, so we're going to do the rated current, 476 amps, and we're going to multiply it by our torque constant, which is 19.81 milli, and that gives us our 9.42 or 93. Well, in this case, 936. So they'd have a little bit less there, but yeah, 9.4, 9.36 listed. So that's how those numbers play together. If you're running it at 40 amps, your maximum 19, we multiply again, 19.81 milli. That means the maximum torque we can get out of this thing while respecting that 40 amp limit is 8.8 Newton meters, so just under 1 Newton meter. That's the power. That's the torque that you can get out of this thing. Okay. I hope that's clear. Okay. So then you got this power distribution hub. So this thing has these rating curves. So if you apply too much, if you ask for too much current out of this thing, it doesn't blow right away. So if you're pulling, actually, let me just discard. I'm going to delete this little yellow circle, and I'm going to draw my own. Let's do it this way. Use the annotation. Pen. Okay. Change the color. Let's use green. Okay, so this is 200%. So that is 80 amps. Now this is the minimum and the maximum curve. So 80 amps could blow it in 2, 3, 4, like 6 seconds, or it could blow it over here in 15 seconds. So there's a little bit of variability in the blow, how long it takes for this breaker to trip. 5 to 10 seconds, 5 to 15 seconds. If you put in more energy, if you ask for more current, you like say, 700, so 7 times 4 is, oh, why am I blanking on that one? 32,
28.
30, 28. A long day.
It's late for us.
I had calls with Indy this morning at 5 o'clock. So anyways, yeah, so then you can see here, there's quite a variation here, but this is right around 1 second, right? And then out here, and these curves, so this is thermal based. So if the ambient air temperature is really high, these will all shift down. You'll get less time. So the more current you ask for out of these systems, and in a higher ambient temperature, the more the quicker it's going to blow out. Okay, I hope that makes sense. And then you've got this circuit breaker. So this is circuit breaker is rated for 120 amps, and again, this has got a pretty good variability between blow times. So at 10 seconds, you could get 200% overrating, or you could get 300% overrating or more. That 200% overrating could last from 10 seconds to 40 seconds, depending on which side of the blow bubble you're at. And again, we can see now the temperature derating impact. So this is set for 25 Celsius right here. Oops. So 25 Celsius. Whoops. And you can see as we move up, so this is 38 degrees, so that's 100 Fahrenheit. It's in this region, you're pretty close, but I mean, it could, when you're dealing with such variability, it could be impactful. It's just something to be aware of. Okay, so let's figure out how we can build a useful model out of this thing. Okay, so what we want to do is take that torque constant and apply it to you build a little circuit that will take that number, multiply it by, so say we want a certain amount of torque, it'll convert that for us to a current, which we can pull from a source, and then we can go and apply that to the mechanical system and see what happens. But then we can track to see if we're going to overblow our current, overblow the main breaker, overblow the power distribution hub. And then also we can maybe think about how maybe we can have some dynamic current limits to be able to respect to maybe provide more power during one cycle, maybe when you're driving, versus another cycle when you need to do more. There could be opportunity to have a dynamic current limit to share current appropriately. So because if we go back, some of these machine robots have a lot of motors on them. Each one can pull up to 40 amps if you want to. So that's only 3 motors running at full power. So how are you going to share that current amongst everybody? That's the fundamental question point. So we'll look at that now. So let's, what's my next slide here? Okay, let's head over to PSIM. Now is a good time to ask questions if you're thinking of questions.
Yeah, we don't have a super huge amount of crowd here, so if you guys have a question but you don't know how to ask it in writing, raise your hand and we can unmute you to ask your question if you want.
So what I've built here is a super simple torque mechanical system. So in PSIM we have, if I open up the library elements here, we've got, we have mechanical loads and sensors, so we can model some very simple mechanical systems like a general torque load or fan load or what have you, or an inertia load. We can measure torque, we can measure speed, and in this case I've just got a constant torque load with a little bit of inertia. And over on this side, this is the electrical side, so I'm applying 12 volts. The battery pack for FIRST is 12 volts, so that's why this is 12. And then what I've done here is I've set up a desired torque amount. I'm dividing it by the torque constant to get the current that will pull. So this source here is a current source down the bottom here, and this is being controlled by a signal. So I'm asking for 0.79 so I'm asking for, hey, that was just my wife. Call. Okay, so I'm asking for, if we do the math here, where's my calculator again? 0.79 times divided by 19.81 milli. And we've got 40, just under 40 amps. Okay, so when we run it, we're going to see 40 amps getting pulled out. And then I've set up a little system here where I will take that current and pass it back out to this mechanical system here. So this little block here is converting electrical energy to mechanical energy through this conversion up here, and I'm getting mechanical power out over here. So this, I hope, is relatively straightforward. So I can run this, and I can see I'm getting just under 8 Newton meters of torque. I can see my main current is 40 amps, and I'm getting, my RPM is slowly spinning up. This is at only over 10 milliseconds, so the very beginnings of an acceleration here, but we can see the RPM start to load up on my mechanical system here. So the mechanical load is super simple in this case. So this is the very beginnings of something very simple, right? So let's do something else here. So I can grab one of these guys. And so this, if we're talking about simple simulations, I can come over here and now I can enable this and I can drop it in, short it up behind. And now what I can do is I can run this, and now I've got an overcurrent flag. So I can run this, and I can see on my overcurrent flag if everyone's happy, sure is. And I can do something like this now where I introduce a step change. Let's ask for another half Newton meter, and we'll ask for it halfway through the simulation. So we'll run this one now. And so right around right at 5 milliseconds, I'm asking for more torque, and we can see my overcurrent flag went up. So we went from 40 Newton meters, let me just delete this screen, 40 Newton meters up to, or 40 amps up to 65 amps. My torque went from 0.8 to 1.25, and the overcurrent flag went up. So this is the beginnings of something on the system level, where we can look to see it at commands impacting or generating overcurrent signals. Okay, so this is a simple system. I have one motor. I have built now a slightly more complex system. Are there any questions about this? Does this make sense? Is this useful? Am I just talking to myself? Are people paying attention?
I'm paying attention. I think it's very interesting. Thank you for explaining everything very well. We have no questions at the moment, no raised hands either, so I'm assuming that everyone is following along.
Yeah, that's just awesome. I really hope that that's the case. Okay, nobody, and the thing with the questions is they're anonymous, so no one will know if you ask a silly question. So I want to make that clear. So now I've got a system here. In this system, I now have 4 motors, and I've converted the motors to be this little subcircuit here so that they don't look as intimidating anymore. Where are we? This guy. So inside of there is my little subcircuit, and let me do this. So we got this. So this is inside of here now. And now I just basically I've repeated it a bunch of times. And now I've got a desired torque control signal being applied to all of them. And what I'm going to do is I'm going to run this simulation, and then down here I've got another one that's is asking for torque, not at the very beginning, but a little bit later on. So I'm going to run this, and we can see that we're pulling right around 40 amps from, this is 39.9 to 39.4 across the first 3 motors. And then on the 4th motor, we can see that I'm also asking for, hang on. Oh, let me change the time basis here. There we are. Okay, so then the 4th motor, I'm stepping up and asking for more torque a little bit later on, right? So we go at 5 milli, I'm asking, and that's stepping in and asking for more. Okay, so, but we have now 4 motors asking for 40 amps, which is an overcurrent. So I can do my 3 main, so there's my 4 overcurrent sensors per motor looking for 40 amps. And then I've also got I've got another one set up over here, which is at 120 amps. So I'm comparing the current measured with the set point here. And when the plus sign is larger than the other side, it'll flip the flag up. So I can come back here and I can go overcurrent main, and we can see that's going from 0 to 1 right around there, and that's corresponding with main current, this guy flipping up and going from 120 amps to 160 amps. So I hope that makes sense. So we're able to see, hey, I asked for too much current there. Individually, the motors were okay, but the system, too much on offer, too much being asked for. So how can we mitigate that? Great question. So what I did is I wrote a little bit of logic, and I'm going to insert that in front of these 2 guys down here. So I wrote a little bit of some C code here, and in the C code, what I'm doing is I've defined that I'm going to measure the commanded torques, and I'm going to enforce a sharing between those 2 motors. I'm going to say, if you 2 are asking for more than your allotment of current, which in this case is 40 amps, I am going to combine. So the 2 of them now, between these 2 motors, they only get 40 amps to share. And they're going to share it 50-50. So I've got my limit of 40. I've got my sharing ratio of 0.5. And I've got now, I'm doing the math. I've got the math here to do this, and I've got a logic statement. So if current sum is greater than the current limit, and torque 1 sharing blah blah blah, I'm going to half the commanded torque to both of them. Otherwise, I'm just going to let it flow through. So if we're over limit, if we're okay, then just continue along. Okay, so let me just delete that line of code. I don't need that. Okay. And we're just going to drop this in. So this is just C code, and I'm just going to drop it in. And we'll wire that up. That one came from over there. And this guy got to come from over here. So we're still going to do this. Whoops. Still going to do this set point. M for torque. So let me run this one now. So what we see now is, and let me just put them all, reduce the total number of things here. We'll put that in the main current over here. Let me delete this screen. Okay, so hope folks see this. So we can see the main current is at 120 amps. It stays at 120. But we can see motors 3 and 4 here are changing. And let me plot motor 3 on this one here. So here's motor 3 in detail. So there's motor 3, it's running at 40 amps. And then once motor 4 asks for current as well, for torque, they automatically shift and change, and we get 20 amps for both of them. We can see our overcurrents are respected now on all 4 motors, and our overcurrent on the main is avoided as well. Okay, and I can do other things here too. Like I could, instead of it being a sharing ratio of 50%, I can make this 75%, and then I can do this when I can 1 minus this. So now one of these guys is going to get 75% of the power, the other guy is going to get 25% of the power. Save, I'll run it again. And now we see that we'll get an unequal, still sharing 40 amps in total, their budget, but now it's being divided differently. So in this case, we can avoid, say you're running your machine and somebody does something command-wise, and that command would result in too much current being pulled. We can enforce limits here, and you can come up with more complex systems as well to force to ensure that the current protections are met. Does this make sense? I thought this would be useful. I hope it's useful. Anybody?
I think we have a shy crowd.
It's my favorite when nobody provides any feedback. I really love it.
Maybe we have to make a test. Like anybody who's listening, put something in the question tab, even if it's just a hello guys, just so we know that everyone's alive. Oh, okay. Somebody said it's cool.
But that's obviously staff because that's your account.
Love your cats listening. It's making sense. Okay, thank you guys. Perfect. It's feeding time, so everyone's hanging out trying to make me feed them. So
yeah,
but okay. Everyone's listening to Albert here.
Yeah, perfect. So next up, so if we go back to my slides, we were dealing with these trip outs. So wouldn't it be nice if we could be a little bit clever? Right? Wouldn't it be nice if we could run with maybe a little bit extra power for a little bit of time and avoid the situation where the breaker trips? So if we could, because I mean, if you see the plot here, let's zoom in, we could get away with a little bit of extra energy here for a little bit of time, 15 seconds or so. That might be significant to have a 15-second boost. In F1, they have DRS, right? What if you could enable DRS by playing with these, by respecting the limits of the thermal limits a little bit? So to accomplish that, we have fuse models. So we can include now, so these guys, I have modeled these curves. So basically, I took these curves and I've loaded them into the simulation. So for the power distribution hub and for the breaker, and what we can do is look to see, so the breaker has a rating of 120 amps. So let me just change that to 120, and this one's got a rating of 40 amps. So let's run this. Oh, I'm actually going to run it for a lot longer. We're going to go boost up the time here 1 millisecond, and we'll simulate it for 200 seconds now. So I'll run this, and we're going to look at these currents down here. Okay, let me make a new window. So we've got the two load currents, just under 120 and just under 40. And what we see from those guys is that there is no problems. We're applying our 100 volts to the load resistor without issue. But if we overload this, for example, say let's go to 240 amps right there. If we run this one now, V6 is the breaker. So at 200%, we've got 10 seconds. And there we go. So right at 10 seconds, we're tripping out. So this fuse model is allowing us to look at if we're able to operate without faults, without tripping the breaker. So if you were clever, I didn't build an example here, but you could now insert this fuse up in there. You can put, and so this one is the PDH blow curve. You can put that one in series with all of these guys now. And, you know, instead of having some really basic logic in here, you could put a timer and track, I've been in an overcurrent state for 10 seconds. That's allowed. And then have a dynamic adjustment. You know, and in this case as well, all I'm doing is limiting these two motors. You know, I've seen some diagrams where there's 10, 11, 12, 13 motors. This could get kind of complex, and I'm not trying to overwhelm you with details at this point, but this decision matrix could become more complex, and basically you can look for yourself to see, you know, on the stimulus that you apply, is it going to be, if you know, in a typical run condition, you'll need to look to see, like, are we pulling the maximum amount of energy out of the breaker that we can? So you have 120 amps. You should probably be using all 120 amps all the time. Can you dynamically adjust based on your, you know, do you need, and then come up, maybe use some more different mechanical loads here to kind of, how much performance benefit do I have? Does this spin up properly? You know, all these sorts of things. There's a lot of stuff that can be done here, and I'm not going to get into those details here, but you know, I'm happy to provide more guidance on this topic in the forum, in the chat, in a public setting as the questions come in. I think some teams have mentors as well, and you know, we're looking to be helpful on this kind of topic. Okay, so this is the end of the FIRST Robotics section, and I'm going to get into so to do what you're doing, what would you expect the learning time for a student could do this? So to do this very basic model here, you can take what I've done. These are Kraken motors that I've modeled here, and they're torque constants. It should be maybe an hour to take this and put in all the motors that you're interested in. You know, if you wanted to focus specifically on certain motors, just leave set some motors at arbitrarily low limits and just be done with them. If you wanted to focus on power sharing on certain motors, you know, this basic logic is C code. I'm not sure what the RoboRio programming language environment is, but this is very simple logic. I would hope that somebody would be able to do this And I would say that the student teams that do manage to figure this out are going to have an advantage versus the other ones, simply put, is my impression on that. And I can make these simulations will be, yeah, so if you can program, so PSIM only runs C code as an interpreter here, but this programming C is, this kind of logic is very straightforward. If you're running Java, then that should be, you know, if you know how to program in one language, it's usually straightforward to kind of pick up the syntax of the other one. And there's this thing called ChatGPT, which is very useful at translating code. So you can make use of chat, of OpenAI and learning language models to come up with the coding properly. So I wanted to skip away from FIRST. So if there's more FIRST questions, please bring them in. So what I wanted to do is kind of get into the more advanced modeling topics.
Okay.
So what we just talked about is the use of a very simple model to replicate the conversion of electrical energy to mechanical energy. For people doing more advanced motor modeling systems approaches, we have the use of fit models. So we're using trained data analytics models to come up with a more complex relationship between drive parameters and operating conditions and the torque that's available. As we can see, motor losses and developed torque are all functions of operating conditions, and it's these complex surfaces, multidimensional surfaces. And this kind of predictive modeling is something that could be accomplished for systems models in Formula SAE or American Solar Challenge or other robotics competitions to better understand how the systems are working together in a more realistic way. So these models would be necessary if you're doing more high performance systems. And so here's an example of a fit model where we've got stimulus, and then we've got a trained AI model in the middle there that then runs out and interacts with the system. And so these models are faster than real time, and they're really quite powerful. There's lots of different things we can do, and there's a lot of content and learning content on this topic. Okay, I see there's more questions have come through. Just trying to make my window bigger. Okay, so I see one question there. May I know what are the major losses in power flow and how can they be minimized? So the main sources of loss in an electric system that uses motors is the inverter and the motor. The way you minimize inverter losses is more expensive switches, so silicon carbide or gallium nitride devices versus IGBTs. This is not something that FIRST kids have to deal with, and it's very it's only something you can optimize if you are designing your own inverter, which I'm not expecting many people will take on. If you're trying to minimize drivetrain efficiency, you know, operating the motor at the efficiency, looking at an efficiency map of the motor and operating it at its most efficient points. So that adjusting your gear ratio would be a good thing to look at to make sure that you're operating in highly efficient zones. So avoiding. Typically, motor drives are less efficient at low speeds and high torques. If you can get out into the main operating range of the machine and kind of stay there, that's going to be a good place to be. Are the motor and breaker presets available for download? Yes, I will make the simulation files available. We'll send them out to we have your emails. You registered, and we'll make them available, and we'll also post them to our academic page. Anything else? Any other questions? So here's this next steps and resources. So look for stuff to show up on these links. Register for that contest that Sarah talked about. And, the community forum for Altair is a place where my team monitors, and we're happy to answer questions there. I hope Yeah.
Yes, so as you see here, we have a page for PSIM. It's called the PSIM Academic Hub. There you can find, other resources on how to learn PSIM if you're a beginner or advanced, doesn't matter. We have lots of links to all different kinds of resources all around PSIM. They're not going to be specific to robotics, like Albert was so kind to build some examples here to show for this workshop specifically. So in the future, hopefully we can develop more of this content, but this is going to be specifically for robotics. Everything else there is general PSIM, how to learn PSIM, how to use PSIM for motor drives and for power converters and all different kinds of stuff. And then, of course, we have the Global Student Contest webpage where you can learn more about the contest, about the prizes, and so on. And then underneath here, the third link is the submission page. On there, you can, see on the right here, I have a little screenshot. You can see the rules. You can see the example videos of, what you could submit and what needs to be in those videos or how long they can be, all of that kind of stuff. And you see also the form on that page. And you see on top of the form, it's asking you if you want to submit already your entry, or if you're just planning to submit during the contest and you want to not forget it, you can click the third checkbox here on the top, telling us you're working on it, and we will send you reminder emails before the deadlines are coming so you don't forget, because we know everyone is busy. And yeah, so there's some pages. I will also find the community link here and post it in the chat so you can see that as well. This is going to be for any student who has any questions to certain products or to our contest. There's certain tags you can use, and you will get your answers from our Altair experts and from our community there.
Thank you so much for coming. Okay.
Okay. Thank you so much, Albert. I think
You're
this
welcome.
was great. We have lots of people who commented in the end after we woke them up a little bit. And yeah, thank you so much for your time, everyone who came. We see here a lot of people say, thank you, Albert, great job. So we all agree. And with that, I think we can wrap up the day and our work today, and, hopefully see you at the next event sometime. And
Everyone
I'm hoping I see all of your submissions.
Thank you.
Okay, have a good night. Bye-bye.